Welcome back to another episode of 7 Minutes with Circuits. My name is MsSiegel and I'm a junior in the Electrical Engineering program at CSU, and I'm currently enrolled in ECE 312 Signals, ECE 332 Circuits, and ECE 342 Electromagnetics. Today we will discuss the signal transmission circuit of a radio system and how it relates to concepts learned in each of the 3 junior year ECE courses. Let's begin with the preamp. The baseband input signal is the actual data that needs to be transmitted, which usually comes from a digital memory storage system, which is then fed to an analog to digital converter. The data can be music, voice, or text. For this example, we will consider the data to be voice, which has a bandwidth of around 20 kHz, up to 30 kHz for hi-fi audio systems. From ECE 332, the preamp stage boosts the baseband input signal, conditions the output to have the correct DC bias for the next stage, and filters out any noise from the amplifier. A simple preamp can be built using a single common source amplifier with a single CMOS chip. A better but more costly preamplifier can be built using a current mirror which sets the bias for a common source amplifier. Next, we will look at the mixer from an ECE 312 signals point of view. The mixer takes the data signal from the preamplifier and a carrier signal from a local oscillator, which is in the megahertz range, and combines them in a way that retains the information from both inputs. This is called modulation. 3 forms of modulation are amplitude modulation, frequency modulation, and phase modulation, each with their own pros and cons. Some examples of these include the AM and FM radio in your car, and phase modulation is used mostly in radar systems. Modulations shift the frequency of the signal so it can transmit at higher data rates, increase transmission efficiency and range, and fit within its designated bandwidth. Modulation also allows multiple signals to be sent at the same time without interference with each other, or other devices to send signals all within a close range without any crosstalk. Shifting back to ECE 332, the output of the mixer is sent to the RF power amplifier. So far, the power of the signal has been on the order of microwatts, and the antenna needs to run on the order of milliwatts, which is 3 orders of magnitude greater than what the mixer can supply. So a power amplifier is needed to prepare the signal for the antenna. To reduce cost and size of the circuit, the power amplifier can actually be designed into the mixer, allowing one CMOS amplifier to function as both the mixer and the power amplifier of this radio circuit. Due to the second order effects of the power amplifier, the output signal contains the modulated signal as well as multiple harmonics of it at other frequencies. These all need to be removed. The bandpass filter is in the next stage before the antenna, which removes all of these unwanted harmonics. The bandpass filter incorporates knowledge from all 3 ECE courses. From ECE 312, we know that the output signal from the power amplifier is a linear combination of the modulated signal and its harmonics. So a well-designed filter can remove all harmonics while leaving the original signal unaffected and clear. To design a bandpass filter, a low-pass filter and a high-pass filter can be connected in series or cascade. The transfer function of the low-pass and high-pass filters are about the same, except for different cutoff frequencies, and if the low-pass filter is a function of S, then the high-pass filter is a function of 1 over S, as seen here. From ECE 332 perspective, we can build either an active or a passive filter. An active filter uses more power and can have sharper cutoffs, allowing for more precision filtering with a higher gain. A passive filter uses regular components such as resistors, inductors, and capacitors to filter out the sound without having any additional gain added. These are not as sharp as active filters and let other frequencies bleed through. A filter that uses capacitors or inductors has an ECE 342 electromagnetics component. Capacitors and inductors store energy, the former by electric fields and the latter with magnetic fields. When the energy oscillates between them is at its greatest, the circuit has reached resonance. The last and most crucial component of the signal transmission circuit is the antenna, which will be viewed from an ECE 342 electromagnetics perspective. For this circuit, we will assume it has a basic Hertzian dipole antenna. As the input signal oscillates, the charges on the antenna move back and forth, which create a varying electric field around the antenna. There is also an oscillating current, which also generates a magnetic field around the antenna. From far enough away, the electric field, the magnetic field, and the direction of propagation are all perpendicular to each other, which is also known as an electromagnetic wave. The shape of the antenna also dictates the radiation pattern and which directions the signal is strongest in, as seen here. Regardless of the shape, the size of the antenna has to match the frequency of the signal that it is transmitting. Higher frequencies require smaller antennas, and lower frequencies require larger antennas. Antenna size is directly proportional to the wavelength of the signal being transmitted. Combining the lessons learned in each of the 3 junior year ECE courses, we were able to fully describe the signal transmission circuit of a radio system. I want to thank you for all your time, and I hope you've enjoyed today's presentation. We will see you on the next installment of 7 Minutes of Circuits. Have a nice day.